Okay, so the next video is all about uncertainties, and this is going to help you score marks in your lab reports in terms of your tables and your processing of your data. It's something that we should always take into consideration, is taking consideration the errors in our experiment. And so one of the errors that comes around actually can come from using our equipment, and we can start looking at our equipment and deciding on equipment error. So there's two types of equipment that we're using. We could be using an analog face, so for example like a clock with a hand that times round. We could have a voltmeter which goes up and has a dial in between. Okay, that would be all kind of analog measurements. The other type that we have is digital, so for example like your stopwatch. That would be a digital piece of equipment, and we considered these in different ways for uncertainties. So going back to analog, okay, we use half the smallest scale of the division. So for example here, if we look at this, if my scale's going up there, my scale's going up 0.1 to 0.2, it's going up 0.1 each time. So if this one, the smallest scale is 0.1, which means that the uncertainty, now we use this little delta symbol, this little triangle here to represent the uncertainty therefore is going to be equal to plus or minus 0.05. Okay, so in this case, I give it to be in half of the smallest scale. Same can be taken with things like your ruler. Okay, on a typical ruler, we can read to the nearest millimetre. Okay, so if I again was having my smallest scale be a millimetre, I would have to take the half of the smallest value. So for the ruler, if I was going along and trying to take a measurement, I would take it to be 1 millimetre. And so the uncertainty is plus or minus, okay, half a millimetre. But sometimes we have to be careful when using rulers when doing our measurement, because when I use a ruler, I use both sides of my ruler, which means that half a millimetre and that half a millimetre come together to give me a total uncertainty for length. Okay, so if I was wanting to measure this length here, okay, the length uncertainty would actually be equal to plus or minus 1 millimetre, because we have plus or minus 0.05 and plus 0.5, and plus or minus 0.5 as well. Okay, so those two get added together to make this one. So when we're using that, you often need to look at your device if you are using an analog piece, and just note down when you do your table, just note down what the smallest increment is and half it to give you your uncertainty there. Okay, so again, remembering that the symbol with the triangle means uncertainty. For digital, it's basically the smallest increment. So for example, let's say you're using a balance, and on your balance it says that it is 0.023 kilograms. Okay, in this case, that 23, that's the smallest increment we can have. That means I have a plus or minus of 0.001 kilograms. Again, if I was using a stopwatch, and it was 0.00 seconds, my uncertainty is plus or minus 0.01 seconds. Okay, so I have with that one there. So again, we're looking at the smallest measurement it can take, and we're just using that as our uncertainty there. Okay. Now, I used a stopwatch there for my last one, which can sometimes be a little bit misleading because we get those stopwatch reaction times, but actually our human reaction times are often a little bit slower than those uncertainties. Okay, so sometimes you might also want to practice your own human reaction time, and it could come out to be maybe about plus or minus 0.3 seconds, which is kind of general human reaction time. So sometimes that's another one to kind of take into consideration, especially if you're having to look and then look at a different piece of equipment before stopping your stopwatch. There is some time there that you might want to consider. Another way of accounting for that, or actually accounting for anything if you are doing multiple trials, is you could also use another method, which is the range divided by 2. Now you have to be careful with this because sometimes that gives you no uncertainty, but you've still got equipment uncertainty to think about. Okay, so sometimes you want to compare this value to your equipment uncertainty to see if it's more or less. So for doing the range over 2, it's just as it says. Well, let's say I've got trial 1, trial 2, trial 3. I'm going to add them together and divide by 3 to get my average. Okay, so I have 1.2, 1.0, 1.4. So my average trial is 1.2. I'm then going to take my range. So I'm going to take my biggest value away from my smallest value. And that's going to give me 0.4. You can also do that really nicely by using a formula on spreadsheet. Simply then divide that value by 2, and that's going to give you plus or minus 0.2, and that's your uncertainty of your trials. Okay, again, looking at this bottom one, 2.1, 2.3, 2.2. So my average is 2.2. The range this time was 0.2. So my range divided by 2 for this, okay, is going to just be 0.1. So that's another way that we can use to calculate uncertainties. Okay, but again, with this one, let's say this was coming out to be 0.1, but my equipment was actually 0.2, I still would use 0.2 there. So the next bit is sometimes with the uncertainties, we actually have to do a little bit more than just figuring them out. We also have to process them. And that's especially important when we're doing calculations. Okay, so we're going to do the easy one first, and then we're going to do the second one, which is a little bit harder. And that's really only appropriate when we're doing like diploma level. But if you're in grade 9 and grade 10, it's really nice to start practicing using this, because I do find that the grade 11s and grade 12s do struggle with kind of coming to this for the first time. So if we're going to be calculating a value, we also have to calculate the uncertainty. So let's say I have two different values. I've got value A and value B. Okay, that could correspond to anything. It could be time, it could be length. I may be having to add two different times together. I might be having to add two different lengths together. I don't know. So in the situation that I've got to add them, it's really simple. So A plus B is equal to C. Well, if I know the uncertainty of A and I know the uncertainty of B, I can then figure out the uncertainty of the answer C. I just simply add the two of them together. So the uncertainty of C is equal to the uncertainty of A added to the uncertainty of B. Okay, so if the uncertainty of A, let's say that was 0.1, and the uncertainty for B was 0.2, the uncertainty of C is going to be 0.3. I simply add the two together there. It's also exactly the same for subtraction. So let's say in this case, A minus B equals to C. It's exactly the same. The uncertainty of C is the addition of the uncertainty of A plus the uncertainty of B. So again, let's say the uncertainty of A was 0.5 and the uncertainty for B was also 0.5. The uncertainty for C is going to be 1. Again, just remembering you want to keep your plus and minus signs as well in there, so that you've got those to represent them being an uncertainty. And just as you can see here, I've put the delta sign, so delta C, showing that's the uncertainty for C. So for addition and subtraction, we're really nice and easy. We just have to add them up, okay? If I had to add them up and then divide by 3, I just have to then divide my other values as well then by 3, okay? So for example, if I was doing my trials, I could add my 3 uncertainties together and then divide them all by 3 in that case. So the next bit is the tricky bit, and this is getting advanced now. So this is when this time I actually have to multiply some values. So I could be doing things like resistance. So resistance could be resistance is voltage divided by current. I could also be doing things like voltage is resistance times current. Okay, so I'm talking about multiplication, and I'm talking about divisions as well. Okay, so in this case, it's multiplications and divisions. I should have said that at the beginning, sorry. Other things as well that we often maybe have to use, it could be things like power, calculating power, maybe it's current times voltage. So lots of different equations that we might want to work out from some of our data. Okay, now if we do A times B is equal to C, we don't add the uncertainty, we actually add something called the fractional uncertainty. So the fractional uncertainty for A is the uncertainty of A divided by A. Okay, so that's the fractional uncertainty for A. The fractional uncertainty for B is the uncertainty of B divided by B. So if I look at it as a formula, this is my formula that I get. It's the fractional uncertainty of C is equal to the fractional uncertainty of A plus the fractional uncertainty for B. So I'm going to do an example underneath just to kind of show you how this would work. So let's say I was trying to work out the distance and I'd measured the speed of my object and I'd measured the time it took for it to move. In this case, I'm going to tell you that the speed is 5 meters per second plus or minus 0.5. My time is 1.2 seconds plus or minus 0.1. Well, if I do speed times time, that gives me 6 meters for D. So I could just times those two together. But I want to now know what the uncertainty is. So I go back and I say, here's my fractional uncertainty rule. The fractional uncertainty of D is equal to the fractional uncertainty of my velocity plus my fractional uncertainty of my time. Okay, in this case, I want to find out the uncertainty. So I'm going to bring my D, my distance, up and multiply that by everything on the top, which gives me the equation down here. So the uncertainty of D is equal to D multiplied by the addition of the two fractional uncertainties there. So in this case, it's 6 lots of 0.5 divided by 5 plus 0.1 divided by 1.2, which is equal to 1.1 meters. So my uncertainty becomes 1.1 meters up there. All right. Again, with uncertainties, you want to keep them small. So usually keep them to 1 or 2 significant figures. You don't want to be making them really, really long and really, really large. Okay, so just 1 or 2 significant figures for your uncertainties. So multiplication and division, we add the fractional uncertainty for both of these. All right, and let me know if you have